So a Boolean function is like any other algebraic function expressed as a function of a list of variables with a corresponding equivalent Boolean expression to evaluate the function values. Okay, so a function like any other algebraic function, we followed by variables, but these variables, for example here x, y, z, they are Boolean variables. That means this variable can pick up a value either 0 or 1. Okay, true or false or true. And then this is the left hand side, and on the right hand side we have a Boolean algebraic expression, which is combination of those variables and Boolean operations. So here it is like x and not of y or z. Now each part of the right hand side term of the equation is called right hand side is called a term. Okay, so here in this example, the x, y bar, okay, y tick, we call it y bar frequently. So it's a term, z is another term, and also within this x and y bar, this is x is also a term, and thus y bar. So, or y not, whatever you want to call it, whatever is more appealing to you, y bar or y not. Something like that. But their point is this: these are all called a term. Z is a term, y bar is a term, x is a term, x y bar is a term, and so on and so forth. Now let's talk about the truth table. So Boolean functions, unlike algebraic also can be doing the similar way, but point is that sometimes we expresses Boolean functions as a truth table. So one thing you need to be clear here, like either it's an alternate representation of a function. It is not that we always derive truth table out of a function and so on and so forth. So it's either way, right? Either a function is represented as a Boolean expression or a truth table. Okay, like algebraic function, you usually do it for how do I say? Do it as an algebraic expression, but you don't see often that an algebraic function is expressed as a table, right? One reason is that a variable in the Boolean algebraic function can take infinite number of values, right? Its range is infinite. It can pick up any values, right? It's any integer or float or anything like that. But for Boolean, we have an advantage that we know each variable picks up only either of one values. Either it is a false or true, represented as 0 or 1. So I can also opt for construct a truth table, which tells me explicitly for each combination of values for these variables, what is my outcome, what is my function value. Okay, so this is the reason we go with we can represent a Boolean function with a table format. Okay, not only just always an expression. And why it is important, why we want to do it? Sometimes from the real life problem, when you are trying to build a digital circuit, it is often easier to first construct a truth table from the problem description and then convert this truth table into a logical expression to build up a logic circuit. So that's the main reason we want to study and have these truth table format of a function. So at this point, what you need to be very clear that a function, a Boolean function, can be represented in two forms, right? One is either with an expression, with a Boolean expression. Other format is a truth table format. And a truth table format contains what? It's a table. It contains all the variables involved in that function, and the last, like rightmost column, is the outcome of the function. So in the left three columns in this example, we write explicitly all the combinations of logical values that can happen with three variables, which is like, for in this case 2 to the power 3, which is 8 different combination can come up. It is a mathematical permutation combination problem. If you solve that okay, with three things which can pick up two different values, how many unique pattern you can generate. Okay, that kind of combination problem here. So that results down to 2 to the power n. If it is there is a n such variable, we have 2 to the power n rows. Okay, we will have 2 to the power n combination. So in this example, we have three variables. So we have 2 to the power 3, 8 rows, and we write down all the unique bit pattern in that table, and then the rightmost column has the outcome of that function for that specific combination of Boolean values of the related variables. Now accordingly, so we can also create truth table for the basic Boolean operations, right? So if it is a AND, then you will see like AND function, if you recall, it's 0, 0 is 0. So basically outcome is always 0, except if my related variables are both are true or both has the logical value 1. Or is a different thing, it is only 0 if both of them are false or both of them have the 0 value, otherwise it's true. An inverter function is very simple. If my input is 0 or if my variable value is 0, outcome is 1, and if it is 1, then outcome is 0. Now let's look at two definition. Okay, now let's look at two definition. Okay, so one is called dual, another is called complement. So a concept of the dual we won't be using much in this context, like digital design context, but complement, you need to be very careful of the complement, what we mean by a function complement, and so on and so forth. So let's start with dual. A dual by definition is a Boolean function obtained by replacing AND to OR and OR to AND in the original function. So it is a transform of a function. Okay, dual is a transform of a given function which is obtained by replacing AND to OR and OR to AND. Also, any function involving a constant value 0 or 1 we interchange to. Like if a function is involved with a value constant 0, we change it to 1, and vice versa. So an example of a function is something like this: xyz with xy or x bar z or yz. And by the way, sometimes we omit to put a dot, so don't think this is xy is one variable. It is x dot y. So dot is kind of we omit sometimes for writing speed and things like that. So you should be familiar with that part. Okay, this is really an AND operation. This is x and y. Anyway, so this function is x and y, or x bar and z, or y and z. So dual, what we'll do, will replace these dots, invisible dots here, into plus, which is, we should not call it a plus, it's a or, and invisible this and operation, we turn it to or, and this or operations into a and, which again we omit the dot in this part. So x and y become x or y, x bar and z become x bar or z, y and z become y or z, and then all these or operations becomes a and term. All right, now let's look at the complement. Complement is very much similar to the dual. Okay, complement, it's again a transformation function. It is a transform of a given function. So complement transform works in this way. It's a Boolean function of a given function obtained by changing ones to zeros and zeros to ones, just like in the dual. And this means, like dual, all the AND is changed to OR and OR is changed to AND. But unlike the dual, variables are also complemented. Okay, if there is a complemented variable like x bar, we call it x in the complemented function. So now example, function xyz, okay, let's say it is x bar and y and z bar, or x bar and y bar and z. Then its complemented function, which we write that a f bar of xyz. So this guy is more, we know that it is coming from a function f, which is x or y bar or z and x or y or z bar. So notice here x bar is transformed into x. So we complement the variable. So if it is a complemented, already complemented, we just write its true form, not uncomplemented form. Otherwise, we complement the form. So this is the complement transform of a given function.